welcome back. So, this is the last lecture of week 2. In this lecture, we want to summarize various digital current mode control architecture that we have learned in this week 2, and I will talk first, I will summarize various digital current mode control architecture, then some fixed frequency digital current mode control, variable frequency digital current mode control, and some aspect of application. Then if we take digital current mode control architecture, so this architecture can be classified based on two modulation technique, fundamental modulation. One is fixed frequency current mode control, another is the variable. So, under fixed frequency we have peak current mode control, and that also have mixed signal peak current mode control, full digital peak current mode control. Then we can also have valley current mode control and average current mode control architecture. And all this architecture, since it operate under fixed switching frequency, so we generally use uniform sampling. Under variable frequency current mode control, the constant on time current mode control, which is analogous to valley current mode control, and the constant off time is analogous to peak current mode control. Okay, and hysteresis current mode control we can configure to peak, valley as well as average, and this is very fast current mode control. So, these are the current mode control basic architecture we have discussed, and we just want to summarize that under peak current mode control fixed frequency, we need a fixed frequency called clock, and this is under trailing edge modulation, trailing edge PWM. Then it is like a peak current mode control structure, and we know that we need to provide delay for computation and conversion computation. We have also discussed valley current mode control, and which is leading edge modulation, and all are under fixed frequency control. And this is the waveform where we know that whenever the clock edge comes, the switch turns off, and switch turn on when the inductor hit the valley current. And here also you should provide some delay for conversion and computation. Then we also know average current mode control architecture. So, this is quite standard, we are only keeping the voltage loop in digital, but there are other architecture, advanced architecture, where by fully digital current mode control, in fact you can take care of the whole thing in the digital domain, but we are not discussing in this course because we are first introducing the basic digital control architecture. But anything advanced, if you can think of, or you can refer research paper, but we are not discussing those advanced technique here. So, average current mode control, it is standard, that means if you take this analog block, it is exactly identical to the standard average current mode control technique that we have discussed in our earlier course. Here only difference, the reference current is coming through digital. Why it is important? Because if you are talking about, for example, power factor character circuit, maybe other controller, low bandwidth controller. So, this current difference should also come from, because we need to also track the input voltage profile, because we need to achieve unity power factor. So, for this kind of application, this analog digital voltage loop is very useful in order to digitize and to retain the ripple, that means the line frequency information, so that our inductor current average value can track it. Okay, and this is very much used in average current mode control, is very much used in power factor character network. But if you go for advanced digital average current mode control technique, where, because what is the problem in this technique? Because your current loop in the analog domain and we are using a low pass filter, so we have to compromise the current loop bandwidth because of the low bandwidth, the low pass filter bandwidth is low. As a result, the voltage loop bandwidth will also be lower. While these are good for PFC, where your outer loop bandwidth requirement is not significantly high, but if you are going for multi-phase and other converter, then you have very high bandwidth. So, such architectures are not scalable there. So, there are alternative fully digital solution, but again these are in the research topic. So, here if we talk about the fully digital mixed signal, again the average current, and it is compared with the reference current, and there is an analog PI controller. Okay, and if we are tracking and sinusoid signal, then we may have to use something called PR controller. So basically it is coming from the internal model control. So if you track a step IREF current, then PI controller is good enough. But if you are trying to track a sinusoid current, then the controller should have the component. If you take the Laplace transform of the sinusoid, that particular component should be there in the controller. But typically people use PI controller because this IREF, if it is a line frequency, it is almost very slow. It is so slow, that means your switching frequency is very high. So your simple PI controller is good enough. That is why most of the commercial products simply use PI controller for the current loop. Now if you are going for mixed signal constant on time control, again it is analogous to valley current mode control, but here the on time is fixed. That is the result. There is no problem with the stability in the current loop. But in valley current mode control, regular fixed frequency control, we know that it is unstable, current loop is unstable for D less than 0.5, and for peak current mode control, we know the current loop is unstable for D greater than 0.5. But in fact, this 50% duty ratio range can also get reduced because of the closed outer loop. But in case of this constant on time or off time control, there is no problem with the current loop stability. So we have discussed this architecture. Then we have also discussed the constant off time current mode control, where we are generating the current reference from the outer loop, voltage loop, and we are converting this that means where digital peak reference is converted into the analog reference by means of a D2A converter, and then we can do, and here it is 1 cycle delay we are providing to provide sufficient delay in the ADC conversion and computational time. Okay. We have also discussed in the previous two lectures about the hysteresis control. So if you straight use a mixed signal hysteresis, then actually it is not effective in terms of utilization of the D2A and A2D, because we cannot use 2 D2A converter or 2 comparator. So this can be simplified, that means the whole block, this whole block can be replaced by this using a single D2A as well as a single comparator. Okay, and we can reduce that resource requirement, and we can make a very fast mixed signal hysteresis control. But now the question is, if we are going for digital, we have now talked about various digital current mode control. Now I want to ask, what technique will be suitable for low duty ratio operation, and this is for, let us say we are talking about 12 to 1 volt POL. It is basically POL converter, which is a standard buck converter, Why POL? Because it is called point of load converter. It is directly supplying to a load, okay, and input is a 12 volt. So here the duty ratio is low. For such low duty ratio operation, for this kind of example, which one will be suitable? In order to understand, if I draw the buck converter itself, so I am just drawing the ideal buck converter, and if we take the inductor current waveform, okay, so this is the structure, and if you take resistive load, and this is our output voltage, and this is our inductor current. Now we need to sense the inductor current, right? So suppose if I draw the inductor current waveform, okay, so let me put it, because your duty ratio is very low, so it is better to use like this. Now you will see the interval for on time, that means is very low. This on time interval is low. This is a low or smaller, and here it is longer. So here I will say it is shorter. Instead of low, I will say it is shorter. It is shorter, and this is longer. This duration is longer, and this is shorter. So that means if it is shorter duration, if you want to implement, and there will be always like a practical noise in the current, practical noise will be there. So if you want to implement peak current mode control logic, so that means in case of if I talk about this current reference, right? I am talking about the analog current. So, this is my analog current, and let us say I am talking about a reference current. If I do any peak current mode architecture reference current, that means I need to take the action within this shorter duration, and that is a very difficult task. So, as a result, for low duty ratio operation, such, because if you are talking about, let us say 10 megahertz switching converter, 10 megahertz, that means your time period is 100 nanosecond, and if you take what is my on time, so on time will be 100 nanosecond divided by 12, because it is 1:12, that much nanosecond, which will be roughly 8 point, I will say 3 something like that, and that is too small, because you need to take comparator action, sensing and all, and you need to blank some of this period because of noise. So, you will end up with a very, very tough problem, and you need a very high speed comparator, and that will consume a lot of power. But imagine we have a long duration of this off time. So, that means if you go by peak current mode control, the problem is this feasibility is a problem, because we know the peak current mode control is very good. I mean, I would say there is no stability problem for low duty ratio, but there is an implementation issue. So, you may not be able to implement. But if you go for valley current mode architecture, it is unstable for duty ratio less than 0.5. So, it is not possible. So, for such application, we go for constant on time control, because in constant on time control, it is analogous to valley current mode control. We have a long off time, and since there is no current loop stability problem in constant on time, so most of the commercial product goes for constant on time control. But if we talk about a boost converter, and also it is easy to sense the low side current of a buck converter, because you can put a small resistance here. So, it is also implementation points of this, it is easy, and that is why majority of the multi-phase low voltage high current product, they go by constant on time, because it is easy to sense the low side current, and they can take the advantage of this current loop stability, but it comes with a price, because your time period will vary. So, in order to adjust the switching frequency, you can keep some digital loop, because anyway the timer can be digital. So, you can just adjust those timing parameter without even having a digital control. But here the advantage, by means of digital control, this valley current reference, then when it enter into discontinuous conduction mode, then you cannot use a valley current, because the DCM current will be 0. So, you need to go for a voltage based approach in light load. Even people go for current based approach in light load for PFM, if you keep the peak current fix and go by this, it is analogous to constant on time control for a particular input voltage condition. So, we will discuss some of this aspect when you go for multi-mode control design, but for the time being we are only emphasizing for low duty ratio operation, constant on time is a very, very popular solution. But if you go to hysteresis control, again the hysteresis control, you need to sense the full current, right? So, full current. So, it is again a problematic for this region, and anything sensing full current, that means you have to do something with the inductor path. So, there are many current sensing technique like called DCR sensing, you can put a resistance, but putting a physical resistance will incur losses. So, full current sensing is not so easy, and sometimes in most of the time it may not be practically recommended. So, that means the selection of hysteresis control is something you have to be careful. Okay. If you are going for very high bandwidth hysteresis, high frequency hysteresis control, then the challenges will be the current sensing. But even if you can implement a high bandwidth current sensor, you still have the problem during the on time the comparator, because of the very smaller time. So, that is why for low duty ratio operation, hysteresis control may not be a very attractive solution, and by default the constant on time remains a very popular solution. If you go for wide duty ratio operation, that means here I am talking about the low duty ratio operation. Similar thing can happen for high duty ratio operation, where constant on time may not be a preferable solution. So, then you have to go for constant off time solution. But if you are going for wide duty ratio operation, but we have to remember, if you are talking about a high duty ratio, let us say high duty ratio, how the high duty ratio is not desirable for a boost converter, because you may not get actually the acceptable voltage gain, because boost converter after certain gain it start falling due to the parasitic drop. And also high duty ratio boost converter suffer from a poor bandwidth due to the right of plane 0, because it comes closer to the imaginary axis. But if you are going for high duty ratio buck converter, the efficiency will go up, because as the output voltage comes closer to the input voltage, the direct power flow will increase and the switching power flow will get reduced. So, as a result your efficiency can improve. So, there are certain applications where you may need high duty ratio operation. Let us say you can talk about 5 to 3.3 volt operation. So, there are many such applications are possible, or your battery voltage is 4.2 and you need to adjust 3.3 volt or other day, because when you are talking about your USB the driver. So, what is the voltage level of this or type C charger, like type C charger. So, what is the voltage level? So, there are different voltage level for different application. Let us say in a mobile phone, processor requires some voltage, then your connector type C USB connector requires some other voltage. So, different voltage levels are required. So, based on that we have to decide which control strategy is suitable. For wide duty ratio operation, for example, is a class D audio amplifier. Class D audio amplifier. In fact, this application is quite similar to our full bridge inverter, because if you are talking about a full bridge inverter circuit, we are talking about a full bridge inverter circuit. So, this DC link voltage like VDD, and we are tapping from here these 2 points, right. Now, if we think of, suppose if we are talking about the load, so it may look like for class D audio amplifier, this will have inductor, this will have capacitor. So, each of this terminal ground, and again this side it is the loudspeaker load, again there the inductor, here will be a capacitor, and this point is connected here. So, differential connection, and this is your loudspeaker. So, in this configuration from either side it is like a buck operation, where if you take the voltage across this point and voltage across this point. So, this is like a V1 terminal and V2 terminal. So, at V1 terminal we need a fixed voltage, and on top of that you have to generate this kind of voltage with the average value of some VDC, some average value, some V average. The other terminal, because this is V1, so this is I am talking about V1, my V1 voltage, we have to generate like this. My V2 voltage should have the same DC level, so that it can completely eliminate. That means, this is my red one, is this V1, that is the average value. Now, suppose if I take the green waveform, and since these two are the different signal across this, so that means the loudspeaker voltage we will see V1 minus V2, right. So, we need to have a green signal which will be just anti-phase with this, and this level also should match, so that they will cancel the DC and their difference will actually create an AC, right. Because if we take, then it will be just twice of this, the amplitude will be twice of this. So, if this is my Vm and if this is also Vm, so your differential voltage peak will be just twice of that, because you will get the differential voltage, and this is my V2 signal, Now, in between there will be switching, that means I am just not showing the internal waveform. So, the inductor current, in order to achieve a wide duty ratio, that means for a one particular voltage level, if I take just a V1 voltage of this of the converter, suppose if I want to show the current associated with this IL1. So, the current has like a current average will dynamics will look like this. That means, actually the average current should be a sinusoid, it looks sinusoid, sorry. So, it should be, it should erase this point. So, if I draw this current, the current should look like average profile like this, and on top of that your inductor current this kind of profile, and there can be wide duty ratio variation, because the output voltage has to swing. Each of these case output voltage has to swing in a larger, it is both side terminal voltage are positive, but it will swing between a large variation and the DC value. So, as a result your duty ratio will be large, and you need to select the suitable control architecture to make the current loop stable. If the current loop become unstable, then subharmonic will happen, and this may cause distortion in the differential voltage, and that will cause noise and other signals. So, it will distort the audio signal. So, such application, why duty ratio happens, one of the application, the suitable selection of these current control techniques are very, very important. So, in summary, we have discussed various digital current mode control architecture. We talked about fixed frequency digital current mode control using uniform sampling, variable frequency digital current mode control using event based sampling, and we discussed some aspect of application of digital current mode control method, and we have discussed some potential solution. And in the subsequent lecture, we are going to implement this digital control architecture, both voltage and current mode control using MATLAB. And then at the end of this course, we will also implement hardware. We want to implement this control logic in actual hardware platform. So, with this I want to finish it here. Thank you very much.